LLMs, language models, DP, differential privacy, these are words we hear quite often in this space these days, right? Well, certainly we've heard it many times during the talks yesterday for those of you who were here. So that said, can we start off by getting a quick show of hands who here have known of a differential privacy DP system being used at their company or university in some shape or form? Okay, a reasonable amount of people. Who here then have took part or is taking part in building those systems? Okay, cool. Well, either way, with all the advances that's been going on in the DP realm and seeing how pretty much everyone and their dog has been trying to incorporate LLMs into their work these days, our talk, which presents how we leverage LLMs to perform privacy red teaming on systems with DP, should be of relevance to you. Specifically, LLMs allowed us to enhance our simulations of membership inference and re-identification attacks on a notable DP system.
As we all know, new LLMs are popping up every month, or at this point, every other week. So, in this rapidly improving landscape of state-of-the-art performances, have you stopped to consider whether these powerful foundation models could be used as strong attack vectors? And then, how would you know whether your DP system might be vulnerable to these LLM-based attacks? Most likely, any case where the inputs and or outputs you're dealing with are linguistic in nature, you might want to consider this. Aside from familiar chatbots, another example of a system that may be vulnerable is the one that is trained to map, say, URLs to topics. Not sure if this rings a bell to anyone, but it's referring to the Topics API, which is a part of Google's Privacy Sandbox initiative. We wanted to experiment with LLM-enhanced privacy red teaming and ideally wanted a relatively new implementation, which is still in the works, that involves linguistic inputs and outputs to apply this on. And Topics match this criteria. As for what Topics does, it functions by first selecting the top 5 most frequent topics per user at the end of each epoch, using both a predefined static mapping of domains to topics, or if not present, using BERT, a language model which is used to assign relevant topics to the domains. When an advertiser uses the API, they receive an array of up to 3 topics selected randomly based on the user from the last 3 epochs. Here, an epoch refers to a week worth of browsing history of the user. The API either randomly selects a topic from the entire taxonomy of 349 topics with a 5% probability of noise, which we call a noisy topic, or chooses a relevant topic from the 300, chooses a relevant topic. Relevant topic from the user's top topics and the other 95% of the time. Additionally, to ensure accuracy, a topic is shared with the advertiser only if the user has actually visited the website at the time of the topic evaluated during the topic period.
The first threat model we explore with Topics is membership inference attacks. So in the case of Topics, if an adversary can successfully identify which topics are noisy, they're effectively inferring information about the absence of certain user interests in the underlying dataset that was used to generate the topic distributions. This capability can be particularly concerning in the privacy standpoint because it allows an attacker to deduce which interests are genuinely associated with the user based on the discrepancies between the expected noisy topics and those actually returned by the API. As a result, this undermines the randomness of DP and the privacy-preserving intent of injecting noise into these topics, making it possible now to learn about the user's real interests. On the screen here is a brief idea of how our MIA simulations were performed. For each of the models, so we ran this simulation through a few different models, as will be discussed later. We let it take 3 topics of the user as input and have it return 3 binary outputs. 0 would mean that it is a normal user topic associated with a real user, while 1 would indicate that it is a noisy topic of our interest in this case. Our MIA simulations, done using the 4 different models, as you see in the little tiny font there on the screen, show that hierarchical BERT performed the best, achieving up to 95.41% accuracy when identifying a noisy topic in the list. This shows that the noise injected into the topic list may actually not be very effective when faced against threat models like LLMs. So we're going to talk about that through revisiting another threat model.
Now that we have noise identification done, another threat model that we explored is re-identification attack, which aim to verify whether users can be identified in a simulated web browsing situation, where we assume the worst case scenario, which is commonly taken for security and privacy context. Here, that means a universal advertiser, that is one ad provider present on all websites. The advertiser receives users 3 topics from the API. This, in essence, is different from the threat model presented in the topics white paper. However, it was something which we were interested in from a red teaming privacy perspective to use LLMs as attack vectors. Here's our attack template from the re-ID attack. Given any model, if the model outputs 0, the historical topic is set is considered not to be correlated to the user's given current topics. But if the model outputs 1, it would show strong correlation and thus re-identification. We used the same 4 models for the experiment, like our membership inference attack, giving the results. Here, box in red, hierarchical BERT again outperformed the others, achieving up to 68.19% accuracy, which can be alarming.
So aside from that, we also did some exploratory analysis on the 349 topics, which has recently been increased. But like at the time, it was 349 topics specified in the taxonomy of the topics API. Since these topics are represented as strings, we employed various embedding algorithms to gain deeper insights into cases where a user with certain unique interests might be even easier to re-identify simply based on these vectors. For this, we use clustering, specifically dbScan, across the topics to better understand the space. When a user's interests align with a cluster containing fewer members, they have a higher chance of being detectable. We refer to this as niche topic detection. We observed that different encoders, or rather across different encoders, we can identify certain topic or groups of topics like news and pets and animals into their isolated clusters consistently, meaning users who have said interests or these specific interests can be more easily re-identified or rather isolated using the embedding or the latent space without any fine-tuning. Now, for edge cases, we try to show that this may undermine the k-anonymity that topics aims for. Our analysis involves the glove embedding technique. From the word cloud here, we can see that certain topics like reference, shopping, flowers, and within games, billiards, are some edge cases. The distinctiveness of these unclustered topics or anomalies significantly increases the potential for adversaries to isolate individuals based on these unique interests. We figured out that there are no topics similar to these specifically within that 349 context. This heightens the risks of re-identification. Going over this, especially with the new increase in the number of topics, we see that it could lead to more unique combinations, which could lead to higher fingerprinting. Finally, we wanted to note that our work was performed on a dataset collected of around 2,000 users from Germany who have volunteered to share their desktop browsing histories in exchange for a financial compensation. This is the German browsing dataset. It has been shared online by researchers and also replicated in other published papers on the topics API. Considering Google's topics scales to 1 billion users, this work is a preliminary examination of the topics API, more strongly working as a proof of concept for LLM-based attack vectors on DP systems rather than specifically for the topics API. As for one of the questions, I believe it's definitely going to be asked where is the LLM is just BERT. Under that, it's still got 0.3 billion parameters if that's what you're looking for. And we did use hierarchical BERT, and we'll be moving on to more open source LLMs like Gemma and Llama in the future. We used BERT, which allowed us to be scalable and our attacks to be run on free compute resources like Kaggle. So thank you, Google. Yeah.